inverses before. I think we talked about them even this year already. Definition of an inverse is the domain and range switch places. And every inverse, when you graph it with its inverse, are reflected about the line y equals x. So I just want to kind of show you how exponential functions and logarithmic functions are related in terms of graphing. So we're going to graph both the exponential function 2 to the x and its inverse, which is log base 2 of x. And I just want to kind of show you how you can pick your points when you're graphing these. We graphed exponential functions back in last week in section 3.1. And exponential functions aren't really that hard to graph because you just pick x values, which are the exponent, you plug them in, and you get the y value. And so we graphed 2 to the x many times last week, so it should be pretty quick to graph this. But then we're going to graph log base 2 of x, and I'll show you how it's a little bit different. I'm going to use blue for this one. And maybe you could graph this without even picking any points, but remember, if you pick negative exponents, it doesn't make the number negative, it just makes it a fraction. So if you pick negative 1, you get 1/2. If you pick 0, any number to the 0 power is always 1. So they all have that common y-intercept of 1, unless they were moved around with the translation. And if you pick 1, you get 2. If you pick 2, you get 4. So one way that you can graph logarithms is you could graph its inverse and then switch it around. I'm not really suggesting that you do that, but you could do that. I just want to show you how these functions look when we graph them. So when I graph negative 1, 1/2, 0, 1, 1, 2, 2, 4, and it's just going to look something like that. Remember that all exponential functions have that horizontal asymptote. If there's no transformation, the horizontal asymptote is the line y equals 0. And this would be an exponential growth model. It's getting bigger over time. Right? We're good with that. Here's what I want to show you for today. When I'm graphing logarithmic functions, you have two options. One option is rewrite it using the definition, like write it as an exponential graph. The other option is just think about what you're doing here. What does x represent in the logarithm? Is the x the exponent? So the x is the answer after you take it to an exponent, right? The exponent is actually the y value. Do you agree with that? And so that's why you could just switch all of these, but probably you're not going to want to make two graphs every time. When I graph logarithms, I start with y values, pick them first, and then plug it in to get the x value. Because think about what this is saying. This is saying 2 to the y, or to the g of x, is equal to x. So instead of picking x's first, why don't we pick y's, and then we would get the x values. Does that make sense of what I'm saying there? So I'm going to pick a y value of negative 1, and if I say 2 to the negative 1, what is the x value that I get there? 1/2. Right? Because 2 to the negative 1 is 1/2. Definition of inverses, the x and y switch places. So my advice to you is pick the y values, maybe, and then work your way backwards. So if I pick 0 for y, I get 1. If you want to pick x values, you have to pick perfect square numbers, or it's never going to work. 2 to some power. But I'm just going to pick 1, and I would get 2, and I'm going to pick 2, and I would get 4. And if you notice, they've all just switched places. So what I want us to figure out is how does that make our graph look different? What's going to happen to the domain and range? What's going to happen to my asymptotes if I switch these around? So I'm going to graph this one in red. And at 1/2, the y value is negative 1. At 1, it's at 0. At 2, it's at 1. At 4, it's at 2. What would be the next point that would work out without being a decimal? If y is 3, what does x become? And then if y is 4, what does x become? 16, and then 32. What's happening is this is going to go up a lot slower, right? Like if I go 1, 2, 3, 4, 5, 6, 7, 8, it only goes up to 3. It's not going to go up to 4 until x is all the way at 16. So it's going to go up very, very slowly here. What about going backwards? Is it ever going to give me a negative x value? Can you ever take the log of a negative number? No. So now our asymptote has changed. Now we can't ever get a negative x, whereas over here we could never get a negative y. So I believe it's going to kind of look like this. This side's going to go up really slow, and this side's going to go down, and it's never going to quite reach 0. So what would my asymptote be? Y equals 0? Should be x equals 0, right? Like it now has a vertical asymptote instead of a horizontal asymptote. So it would have an asymptote of x equaling 0. Like it's never going to reach that point. This side's going to keep going forever. What would the domain of this function be? Of the log function? Including 0? No, like it's never going to equal 0. It's never going to be negative. So the domain of the logarithmic function, if there's not translated, is 0 to infinity. Think about on exponential. The domain was all real numbers. The range was what was restricted. What would the range on the logarithmic function be? The range is going to be all real numbers because every negative number and eventually every positive number. And again, if you look back at what we wrote out about exponential functions, the domain and range have switched places. They're not going to all be as simple as just graphing log 2 of x because we can do those transformations. But I want you to get the basic idea. It always is going to kind of one side go down towards a vertical asymptote and the other side is going to go up. It could be flipped over. But this is the general shape of a log graph. This is the general shape of an exponential graph. So let's look at maybe a little more complicated one. Oh, this was not even more complicated, but that's okay. We'll go with it. We're going to find the domain of this, we're going to find the x-intercept, and we're going to find the vertical asymptote. Every logarithmic function will have a vertical asymptote, just like every exponential function will have a horizontal asymptote. And if I'm graphing this, log base 6, I need powers of 6, right? Like I need it to, my x values are going to all be the answer of 6 to some power. So if you want to pick x's first, tell me a power of 6. 6? Hold on, let's find the y value that goes with 6 first. If I take log 6 of 6, what is the y value? What is the exponent that goes with that? 1, right? 6 to the first equals 6. The x's are your answers, the y's are your exponents. So, it's going to get big very quickly. If I pick 36, then the y value, log 6 of 36, would be 2. The exponent is 2. Can I pick some other points that maybe aren't so big? 1? 0. Think about exponential. Remember with exponential, you always had the point 0, 1? For log graphs, do you agree without any transformation, you're always going to have the point 1, 0 on it? 1/6? What would be the y value that goes with 1/6? Negative 1. I don't want you to make a graph that goes to 36, but I want you to keep that in mind when you graph it. Your graph is not going to reach 2 on the y-axis until x is at 36. That means the bigger your base, the slower that graph is going to increase. So when I graph this, 1/6, negative 1, that's really hard to graph that. 1, 0, I always have this x-intercept here. 6, 1, it's not going to get up here to 2 until 36, which is really far away. So that's what I'm going to look for when I'm grading these. I don't want you to make your graph go to 36, but I don't want your graph to go above 2 either. Does that make sense what I'm saying there? So when I make this line, I shouldn't really make it flat, but it's going to go up very, very slowly. See what I'm saying there? Like, it's not going to actually reach there until 36, and I know it's never going to be negative. Yes? Does that kind of make sense? What would the domain of this be? 0 to infinity, because you can't take the log of a negative number. You can't take the log of 0. We learned that yesterday. What is my x-intercept? 1. Where does it cross the x-axis? And where is my vertical asymptote? X equals 0 is the asymptote. Because isn't it a vertical line that it's never crossing, right? If you have a vertical line, it's x equals horizontal line. For this, y never gets to 0. Like the y values never go to 0. So the asymptote on an exponential is a horizontal line. Horizontal lines are always y equals that number. This is a vertical line. It's never going to go past this number. The x is never going to be 0. It's never going to be anything less than that. So that is a vertical line, and vertical lines are always x equals whatever that value is, which is 0. One more, then I'll give you some summary things to help you. On your homework today, the ones that you're graphing, I believe, are log base 10 and ln, which means if you're okay graphing decimals, can you just use your calculator for log base 10 and ln, and you can plug in whatever number you want. It doesn't have to be a nice perfect square. So that works. I want to show you how we can do this if it wasn't base 10, but then we'll just use our calculator to get some decimals as well. Okay? This one has some stuff going on with it. It has a negative in front of it. What does a negative in front of my function mean? It's going to reflect it. Right? Flips it. And then what about a minus 3 inside the function? What does that do? Moves it to the right. If there's a number outside, it moves it up or down. All those transformations still work, but we can also just pick some points here. So before we jump straight to using our calculator, I want you to think about, if you couldn't use your calculator, what numbers would you have to pick for x?
Bigger than 3.
Well, you're right in that. We definitely have to pick numbers bigger than 3 because we can't take the log of 0. Normally, let's just go over here to the side. If I said log base 10 of x, what would you pick for the x values? What would you pick for x values that you don't need your calculator for?
Oh, perfect squares.
Perfect powers of 10, right? So like I could, if I was going to graph log of x, I could pick 10, and the exponent would be 1. I could pick 100, and the exponent would be 2. You with me on that? But what do I have to pick now that it's x minus 3 in there? Like if I pick 10, I'm going to have log of 7, and I don't know that off the top of my head.
Log is 6.
So you have to pick numbers that when you subtract 3 from it, that makes it a perfect square. So Sarah says 13. If I plug 13 in here, look what I would have. I would have negative log of 13 minus 3, which would be 10. You see why you pick 13? What is log base 10 of 10? 1, but a negative in front means I actually would get negative 1.
103.
103. I definitely don't want to graph that. But 103 would be negative log of 100. And what would you get? Oh, what about fractions?
You would probably get a positive instead. I guess. 110.
So what am I going to pick? I can't just pick 1/10. What do you do? Some fractions in the head there? What? 3 and a 10th? 3 and a 10th? because 4 minus 3 is just 1, and what is log base 10 and 1? 0. So I just want to show you that you can pick those numbers. Since it's log base 10 though, you can really pick whatever you want. Like I said 7, use your calculator and plug in negative log of 7 minus 3, which would be 4, and your calculator will give you decimal. Do that, Henry. Do negative log of 4. It's going to be an ugly decimal. Did you get an ugly decimal?
Yes.
I want to know that decimal.
-0.602059.
So we're graphing that. I don't really need all those decimals, right? Negative log of 4. It's like negative 0.6. So you can use your calculator if it's log base 10, or if it's ln, use your calculator, because it's all going to be decimals. But I just want to show you that you don't have to. So let's see if we can make a decent graph of this.
Are they all going to be base 10, but we have to do it at home?
Base 10 or ln, I think. But on the worksheet that we're going to do on Friday, I'm going to give you some other bases, because I like when you graph those better. Okay, let's see. 3 and 1/10, 1. 13 negative 1, I'm not going to graph that. 103 negative 2, I'm not going to graph that either. 4, 0. 5, 6, 7, negative 0.6. What am I doing wrong? 4, 5, 6, 7, negative 0.6. Oh yeah, okay, I'm good. Sorry, it's flipped. You're right. I was like, there's something terribly wrong here. And then 13 would get me down here to negative 1. So this, it's going like this now. Do you agree with that? How do I know where my vertical asymptote is? You just set this equal to 0, and whatever you get, that's what's going to make it equal. Like, that's what your asymptote's going to be. When it's just x, it's 0, because you can't take a log of 0. In this case, my asymptote would be 3, which means my graph is never going to cross 3. So what does that make your domain change to?
3, 2, 1, 3.
So again, very similar to exponential functions, but also different, because exponential functions, if it was something outside of it, that's what changed your range, because you were moving it up and down. Domain's what's going to change on these. All right, so definitely you want to have a calculator that you can do log or ln on. If you have a computer, you have a calculator that does log and ln. I think I should have out of this, but I didn't show you guys. If you go to, I think it's under, I have it right here, but if you go to all programs and accessories, you can go to calculator, and normally it looks like this, but if you just hit view scientific, then you have ln and maybe log. So if you don't have a calculator at home, you do have
All computers have this thing.
all under accessories. All computers have those. Well, at least Windows do. I don't know about Mac. I don't have a Mac. But if you have a smartphone, you also have a calculator, because you can get a calculator on there that I believe will be scientific as well. So you definitely need one of those. I have these kind of things if you want to write them down. For log base anything x and ln of x, these are kind of the characteristics that are the parent graphs, and then you can change the parent graphs moving your left, right, up, or down. So we kind of talked about this already, but if you want to write it down, it is in your book. The domain will be always from 0 to infinity, unless it's shifted. Range will always be negative infinity to infinity, because the y value is your exponent, and you can plug in any exponent you want. That's why it's all real numbers. The x-intercept is 1, 0. Unlike exponential, it was the y-intercept. Again, these are increasing and continuous functions. And you will always have a vertical asymptote. If there's no transformation, that asymptote would always be at 0. So again, kind of could add this to our functions that we did back in chapter 2, I think. We should be able to recognize what these functions look like. Yes? have no idea what you're talking about. When I was going over the homework, that's the definition. We wrote that out yesterday. If you have y equals log a of x, by definition, we can say this, if and only if a to the y equals x. That is your base. The y is your exponent. That's why I say a logarithm is an exponent. And the x is always your answer. So when you're graphing these, if you want to write it like this, so then you can pick your y values and get the x values, you're welcome to. Other questions about this? I think this is all my notes. So 37 through 40, those are matching graphs. Try to look, I believe they're transformations. Try to look to see what's happened where it's moved left